So let's start today's tutorial. In today's tutorial, we will go over the topic of HVAC and the boilers. We will go over two questions. One is regarding to the HVAC, another one is about the boilers. So let's see these two questions. These two questions you can easily find at your textbook. So if you can find it, just let me know and I will show you how you can find these questions. So for the first question, how many watt of sensible heat is needed to heat 20 liters per second of 20 degrees Celsius air to 32 degrees Celsius air? So in this question, first of all, you need to identify what is a sensible heat. Sensible heat is the energy, or the power is coming from the temperature difference of the water, of the air, then that will have the energy raise or drop. So it's a kind of sensible heat. Apart from sensible heat, there's another heat which is called the latent heat. Latent heat mainly change the state from liquid state to gas state or solid state to liquid state, from water to vapor. Such energy, we will take it as the latent heat. But in this question, we mainly focus on the sensible heat only. So the sensible heat with the difference in the temperature. So from the equation of the sensible heat, the energy, or here is coming from the power, because for the mass, we are consider the mass flow rate rather than the mass. So with the per unit of the second, so it's a power. So based on the questions, we will have the mass flow rate times the specific heat capacity of the air. Here the media is air, and also times the temperature difference. So we have this equation. So welcome, Sam. Just a moment. Welcome, Sam. Can you hear me?
Hi.
Okay, yeah. Hello, how are you?
I'm good.
So we just start about two questions today. One is about the HVAC, another one is about the boiler. Okay, so another newcomer. Welcome. A moment, just, okay, can you hear me? Welcome. Mr. Fenster, welcome. So today we are going to take a look on two questions. One is from HVAC, another one is from the boiler. So in this question, you may simply find in your textbook. So this question is about how many watt, how many power of sensible heat is needed to heat up 20 liters per second of 20 degrees Celsius air to 32 degrees Celsius. So first of all, you need to identify what is a sensible heat. Sensible heat is the energy or the power, here is the power, which come from the temperature difference of the same media of the substance. Here, we focus on the media is air. So the temperature difference will have the energy drop or energy raise. So here we can obtain the power raise. But another terminology, which is called the latent heat, it is not related to the energy difference. It's just the energy to transform to change of the state. Like if you boil the water, the liquid will change to the vapor. That is the latent heat. But today this question is only focused on the sensible heat. For the sensible heat, the equation is coming from the mass flow rate times the specific heat capacity of the air, the Cp, and times the temperature difference. So here, I would like to show you how this equation transform to the equation of the power equal to the flow rate, the liter per second times 1.2 times the delta T. Why I say this equation? Because you can simply find this equation from your textbook. So I would like to show you the step starting from the original mass times mass flow rate times specific heat capacity times the temperature difference. So you may easily find that I list the terms, the number, and also the unit. By transforming the mass flow rate, I will let the density involved. So the density of the air is 1.204 kilogram per meter cube, and times the liter. I'm not sure you understand or not. 1 liter is equal to 0.01 meter cube. So I make use of these two additional terminology, and which these two parameter multiply each other to become the mass. Also, of course, the flow rate. These three terms. So they are colored in green color, which is easy for you to identify this. And about the specific heat capacity of the air, which is equal to 1.005, and times the temperature difference. So you can simply see that if I can, some of the unit, I can cancel it out. So the remaining unit of this equation, which is equal to Joule over the time, the second. So that is exactly what I need, because we are going to find out the power, the watt. So Joule per second is equal to watt. So if we go through step by step, we can obtain this equation. Once we have this equation, we just simply put the number. Now what number we have? First one, we have the volume flow rate, 20 liter per second, and also the temperature difference. So by this equation, volume flow rate 1.2 is what we have defined here, and the delta T, we have obtained the delta T by 32 subtract 20, then we can have the delta T. So in the next pages, same question, we just put the number in this equation, and we can obtain the power is equal to 288. Any question on this? Any questions?
Yes, can you show the previous slide?
Sorry, I beg your pardon.
Can you show the previous slide? Is that
okay?
Very
okay,
fast.
no problem.
So
no problem. Okay, this one. Maybe I can explain again and let you have a better understanding on that.
No, just
okay.
the part when the 1.05. Okay, that's the air capacity.
Yes, specific specific heat capacity of the air.
And the delta T is with the given. Okay.
Yeah, it's 32 minus 20.
Okay, yeah, just that. Thank you.
Okay, you're welcome. So any question on? So for this this kind of question, you need to understand what is the sensible heat. and what is the equation or what is the formula of the sensible heat? That is the MC delta T. And when we know about the formula we apply is MC delta T, because MC delta T is a mass flow rate, how we can transform this MC delta T to the volumetric flow rate. Because why we need to have a volumetric flow rate? Because what we are given, the number is a volumetric flow rate rather than a mass flow rate, okay?
Yes. And what does LPS stands for?
LPS is a liter per second. That is the volumetric flow rate. Yeah. Because in the book, in your textbook, it doesn't make use of the terms of the flow rate or volumetric flow rate. They just simply stated LPS, that is the liter per second. That is the same terminology of the volumetric flow rate.
Okay, thank you.
Okay, welcome. Any questions? Okay.
No, it's all clear.
Yeah. Oh, okay. So if no, then you can try some of the questions from chapter 8, I mean, and try some more to see if there is any question. If you find any question during your study, you feel free to email me or contact me to see we can share each other. Okay, another chapter is about the boiler. So I would like to know at the left hand side on the screen, do you know how to use this chart? Do you see this chart in your lecture?
Yes, but I don't remember exactly how we.
Okay. So I would like to make use of this question to show you how to make use of this chart to find out the efficiency and how we can make use of the efficiency analysis to find out what we have already gained from the saving. So this question will teach you all about that. Okay, so may I have a little description on the chart at the left-hand side? Here is a chart. We are going to find out the efficiency based on the temperature of the stack and also the flue gas of oxygen percentage. So by making use of the input like the flue gas oxygen, I mean the flue gas of the oxygen contact and the temperature of the stack gases, and we can find out the efficiency. So let's take a look on the questions. Your present system has 10% flue gas oxygen. A new control system is supposed that, a new control system is proposed that will cost 250,000 Canadian dollar, but would reduce it to 3%. So that means less flue gas percentage of oxygen. So how much annual fuel cost will be necessary to justify this expense if your company demands a maximum payback period of 3 years? So assume that the combustion efficiency curve is same as the figure 9-11. 9-11, the figure is exactly what we have. Take a look at the left-hand side. That is the graph I screenshot out and put it in this slide. So in another word, when we need to do the calculation, we need to make use of this chart, okay? So for your concept, 10% fuel gas. What is a fuel gas? Is after the combustion, we call the emission, which is the fuel gas. A moment. Let me admit one more members. Welcome. Let's see. Yeah. Okay. Let her. Yes. Welcome. Welcome. So I believe everybody can hear me, and it is great. And see you all again in this tutorial. Now we are going through another question. Is 9.3 is about the boiler. So for this kind of question, you need to understand is if high percentage of the oxygen, that means you can't make, because the combustion, the element of the combustion, or I can say the combustion triangle, which obtain the fuels or which obtain the oxygen. So higher percentage of the oxygen in the emission gas is not good, because you are not consumed very well on your combustion, because some extra oxygen will remain. If we have lower percentage of the oxygen percent, it will show a better performance of the system. So with this idea, why the system conventionally have 10% fuel gas oxygen, but if you invest 250,000 Canadian dollar, it will reduce to 3%. That means with this lower percentage of the fuel gas of oxygen, you can make your system with high efficiency. Okay, so you need to have this concept. Otherwise, you don't know why. Now only the fuel gas oxygen percent is dropped. But what happened? The result is your system efficiency is increased. Okay. Any question on this concept?
Yes. No. Can you repeat that, like the relationship of the percentage with the efficiency?
Okay. Okay. So for the first term, the fuel gas oxygen, you need to know what is that. The fuel gas oxygen is after the combustion, what is the percentage of the oxygen remains. If there is a higher percentage of oxygen, that means the combustion with extra high oxygen. So where do your oxygen coming from? If you have a boiler, you need to direct the oxygen to your system, right? If more oxygen, that means you need more power to direct the oxygen to your system. After the combustion, if there is still a high level percentage of the fuel gas oxygen, that means some of the oxygen didn't use during the combustion. It's a kind of waste. So when you reduce it, when we find the fuel gas, that means the emission after the combustion, the gas, only 3%. That means you have made use of all the oxygen except 3%. So because every operation in boiling is money, it's investment. Such like how you input the oxygen will not go per your requirement to go to the system. You need to install a pump and draw the air from the atmosphere to your system. So higher power will take you higher energy. So which with higher oxygen, okay, high oxygen content. But if you not fully utilize the oxygen you draw from atmosphere, so it's a kind of waste. If high percentage of the fuel gas, then you are not making use, or you are not using the best combination of the oxygen in your combustion.
Okay, so anytime that the exercise mentioned full gas oxygen is always referred after the combustion.
Yes, yes,
okay.
yes.
And yes, it's always referred like as a waste.
If higher percentage, that means
yes.
But of course, 0 is the best because you make use of all oxygen. But be careful, 0 sometimes may not be the best, because if you have high volume of fuels. You burn the natural gas, but you do not provide sufficient percentage of the oxygen. It also wastes of the fuels.
Yes.
It's an incomplete combustion. Okay. So, but if you exceed the high percentage of the fuel gas oxygen, it also another kind of waste. It's about the energy you drive the pump to drive the oxygen, the air to your system.
Okay.
Okay.
In the case, I don't know, and maybe in the exercise, I haven't checked the exercises, but is it a way when we can identify they are referring to the oxygen before and the oxygen after, or is always referring to the oxygen after the combustion?
Not really, but for this, I would say in this question is about the oxygen, and also for this chart, we also consider the oxygen, because if you have the fuel gas on the percentage of the carbon dioxide, we are not taking this axis as the reference. We will take the horizontal axis. It's about the percentage fuel gas carbon dioxide.
Okay.
But for this question, we don't need to take care of the fuel gas of the carbon dioxide. We just make use the content of the oxygen. Okay.
Yes. So it means that we can be asked for the oxygen or the CO2.
Yes.
Okay.
Yes, will be. But all the times you need to also understand is right now the chart is a carbon dioxide. Mainly the carbon dioxide is a good thing after the combustion. If you have an incomplete combustion, you will generate carbon monoxide rather than the carbon dioxide. You know what I mean? So I'm not sure you have heard any accident like I mean for the old design of the car, if you start the engine and with the closure, close the door, close the window, but the human inside, somehow the combustion, the fuel gas may contain the carbon monoxide. The people will die in the past. But now with a better design on the car, it really not much happen. But in the past, we have heard the accident like that. That is the incomplete combustion, which will have the carbon monoxide, CO, rather than CO2 generate. Then it is a signal of incomplete combustion. But carbon dioxide is a signal is of the complete combustion. Okay.
Okay. Okay.
Okay.
Thank you so much.
You're welcome. So any question on what I explained about the fuel gas percentage? And then you have a concept is why this show a high percentage of the fuel gas oxygen. That means it's not good. If we can lower it down, we have a higher efficiency. That we need to invest the money. We have this story of saving. Okay. Okay, so let's see how we make use of this chart. Okay, so this chart, everyone may know, we need to find out the efficiency, but how we make use of this chart. So per the question, 10% fuel gas oxygen, that means 10% of the oxygen. So we study the action. This axis is the percentage fuel gas oxygen. So the topic is, the question is 10%. So in the 10%, we draw a horizontal line. But how far we need to draw? We draw the line which touch with this curve, then stop. Okay? So after the horizontal line touch with this curve, we draw a vertical line that touch with the stack temperature. So what is the stack temperature? Why I take 250? That is what we take the reference from your textbook figure 9.11. So the stack temperature is 230. That means in your boiler, in your furnace, the temperatures reach 250. So after I touch this curve and I draw another horizontal line to the end. Why I need to the end? Because these three axes represent three different types of fuels. And now in this topic, we are going to find out the natural gas, not number 2 oil, not number 6 oil. Number 6 oil is kind of a heavy oil, but now we just focus on the natural gas. So when we draw a horizontal line, we can reach the number which is approximately equal to 76%. Okay. So any question on how we handle this and how we draw this chart, how we use this chart? Any question on that?
No, just the stack temperature is always given.
Yes.
Oh, okay.
Yes. Because if you don't have this temperature, you don't know how what is the status of the furnace or what is the status of the boiler. Actually, for every in real reality, every boiler will be decided what temperature in servo chamber, so you can know about this number. And of course, in the question, you should know about it. Otherwise, you can't calculate it. So any question on that? Is the base case 10% fuel gas. You haven't changed anything. The old system, 10% fuel gas. Then we can make use of this chart and find out what is the efficiency when we boiling the natural gas. Okay, when you burning, not a boiling, you burning the natural gas. Okay, if no, we see if we make the improvement from the 10% fuel gas oxygen to 3%, what is the situation of 3%? That is the case. So with 3% fuel gas oxygen, we starting here at 3, the number 3, and draw a horizontal line which stop at the point which intersect with this curve. Okay, so after this curve is touched, then we draw a vertical line, because we need to compare the same number of the stack temperature 250. So we draw this vertical line and touch with this line and stop. And in this intersection point, at this intersection point, we draw a horizontal line which point to left and touch with the natural gas. Then we can know about the new system, the improved system with the efficiency of 81. Any question on how we can figure out the efficiency of the new system, which is equal to 81? Okay, if no, then I go to the next page. So we know the baseline efficiency is 76%, and we also know the new efficiency of the system is 81%. Then the difference, I can say the efficiency improvement is 5%. This page is very important. And why is so important? Because if I find 5% efficiency, that is not the ultimate. We need to find the number. Because now in the question, we know if the new control system is proposed, there will be an $250,000 we need to invest. So it's a term of not the energy efficiency, not the performance, is in terms of the saving. Some people is confusing about the saving is equal to efficiency. But I can tell you, saving is not equal to efficiency. Saving may be more than the efficiency. Why? Because we have the same output, but not the same with different input, because the efficiency is output over input. But if what we can calculate the saving, we are focused on the input. So with the same output, we need to find out the change of the input rather than change of output. For the efficiency, we know about the change of output, not the change of input. So there's a difference between the saving percentage and the efficiency percentage. Okay? So here is the equation, but for you to, at that moment, to justify this equation may be a little bit harsh. But I would suggest we'll take a look on this example, okay? This example to let you know the change of efficiency is different from the change of saving. So we, in the saving concept, we assume the output is the same, okay? When we have output is the same, if we input less than before, then we can have a saving. If we input more than the baseline, that means I don't have any saving, okay? So with the same concept of 62, we make use of the efficiency concept, output over input. So that means it will be the denominator, that will be the nominator. 76 over 100 is 76%. That is very easy because we just make use of 100 as the baseline, as the input. So if we have a higher efficiency, that means we theoretically we just input less, then we have a high efficiency if we have the same output. So in the new case, let's assume we have the same output of the heat, 76 gigajoule, with the consideration of the 81% efficiency. When we calculate the input, it is just 93.83. So the saving is 6.17. You can also regard it as a percentage. Okay, let me stop a moment. Why? Because I need to share one of my link, because we will be terminated after 10 minutes. I don't want everybody will frustrated after we are cut. So I have generated another chat room. Once this chat room is cut and terminated, you can use this link and we can continue if we have not finished. Okay. So let me share my screen. Okay. So let's back to the saving percentage. So if we keep the same output, just calculate back to the input, we clearly know that the percentage of efficiency increase doesn't mean we have the same percentage of the saving. Okay. Any question on this concept? Saving percentage is different from the efficiency increase or decrease percentage. Any question?
No, that's
okay.
Clear.
Okay. Then for the next step, for next step, we just summarize what we did. Now we know turn the question. Let's have some review on the question. Company give us indication, or we have this indicator, is this system we need to invest 250,000. It's quite a lot actually. It's 250,000. But if we can have this maximum payback period of 3 years, that means after 3 years, with the summation of every year cash flow, that means every year if I gain, sum of these 3 years gain, then can cover these costs, 250,000. Then I can also go ahead. But because now we know the saving is, we know about the saving percentage, and we take this number is what we have is the saving. That means if 3 years we can have the saving on 250,000, then we can go ahead on this project. So let's see on this logic is 3 years of saving, we can achieve 250,000. Then now 1 year of saving is 6.17. That is what we figured it out here. And with 3 years, that 3 times 6.17% of each year saving times the annual energy use, that is what the number, 250,000. So if I make use of this percentage, 18.51%, that is equal to 250,000. Then just by the proportion, we divide 250,000 by 0.18351. Then this number will give us the annual energy cost we need to achieve in these 3 years. Then we can satisfy the condition. Okay. Any question on that?
How did you calculate the annual energy use?
Oh, I just first of all, we need to have the concept on what is the simple payback period. 3, and for this equation is investment, the cost of the project, that is 250,000 over the denominator is the annual net cash flow. That means the annual saving. Okay, that is the equation. So if we have this number, we will have 3 and 250,000 and divided by 3, we can have 83, 333, blah blah blah, this amount of value. And for this one, why we come up of 18.51 is if every year we have 6.17% saving. If we obtain this as 3 years, we multiply this number by 3, we can obtain 18.51%. Okay, and 18.51%, that we need to fulfill 250,000. So we just calculate this by the proportion. Just you list the number 250 over the total lump sum, okay, and the percentage of 18.51 over 100, then you can obtain this number, okay, this number. Because it involves two concepts. One is the simple payback. Another one is saving and the usage.
Okay, and that was the question, right? Like, which is the annual energy cost?
Yes, the annual energy cost, yes. That is what we need to find out from the questions. How much annual fuel cost will be necessary to justify this expense?
Yes, okay, yes.
Okay. So that is what I need to explain in these two questions. So I'm sorry, because I know some people is come late. I'm sure everyone have listened this question 9.3, but anyone missed this explanation on 8.8? Everybody have also has already listened to this explanation, right? Okay.
Yes.
Okay, that will be great. So today I just go over two questions from two chapters, and as Professor Demopoulos told me, you are going to have a quiz, right?
Yes, and the 31st.
Or 21st, and you need to prepare a cheat sheet, right? A double side A4.
Yes, we can have a sheet.
Okay, 31st, right? Your quiz. When will you have a quiz?
Yeah, March 31st.
31st. Okay. So 9 more days. So a week later. Okay. So during this period, if you have any problem about the questions, any problem about anything which relate to your quizzes. So your quizzes is whole syllabus, starting from the first day of lecture, or what content your quizzes is about?
I don't remember, but I think it's HVA and boilers, yes.
Okay. So if you have